Okay, so we're getting close to the end of the semester, and today's lecture we're going to start to wrap up and also starting our review of the entire semester's topics. And hopefully, we can generate a topic list for the next two video lectures so that when you are doing your review, you can compare to this list and go, well, okay, this topic I'm fully prepared of, and then another topic I'm not exactly 100% sure, so I'm gonna spend time on it. So you trying to create you a checklist here for your own review process. Now, and now, the last little bit of new content that we're trying to wrap up here is called phase diagram. Okay, and this is for different matters, each different matter. Okay, and everybody's pretty familiar with this in your everyday life. Okay, that a given matter could change their physical states. Okay, from solid to liquid, liquid to gas, so on and so forth. And each of the matter will have its own diagram, phase diagram. Okay, and we're going to use water as an example here to generally introduce what a phase diagram look like. Okay, so a phase diagram is a pressure versus temperature graph. So the y-axis is going to be your pressure, and the x-axis is going to be the temperature. Okay, and overall, the area, okay, the xy area is divided by three different lines that kind of crossing each other and cut your area into three different parts. Okay, now the part where you have low temperature and high pressure, which is this area. Okay, this is where solid exists. Okay, now why is it at low pressure and mid to high, low temperature and mid to high pressure? Well, think about water. Okay, you want to have the solid form of water, which is ice. What do you want? You want to have low temperature, cold, okay, to make things freeze, and then you want to have high pressure, okay, because lower pressure gave your water a better chance to escape into, to free up into liquid and solid, and gas. Okay, so this part is solid. This middle part here is liquid. And this high temperature, low pressure parts, of course, is your gas. Yeah. Okay, and where these three lines, okay, the solid liquid interface, the liquid gas interface, and the solid gas interface crossing each other, this point is called triple point of water. Okay, what does that mean? That means at this particular pressure, okay, you don't need to remember the number. I'm going to give you the number. Very low pressure and 0.01 degrees Celsius temperature. Okay, this is where this set of temperature and pressure, so temperature and pressure, where all three phase of water coexist. Now, and now, what good does a phase diagram do? What kind of information can it provide? Okay, one of the very typical thing that you could do with the phase diagram is that you can actually, at a given pressure, let's say right here, let's say this is 1 atmosphere, okay? You could draw a parallel line to the x-axis, the temperature axis, and it's going to cross two interfaces here. The solid-liquid interface, which it cross right here, and the liquid-gas interface, which it cross right here. And now, both of these 2 points represents a particular temperature if you go down straight. Okay, and these 2 temperatures, what are they? You already know what they are. Okay, so look at this phase diagram. What does this mean? Well, this is where at 1 atmosphere, normal pressure, okay, solid turning into liquid. For water, okay, what's solid turning into liquid? Oh, that's ice turning into liquid water, or liquid water turning into ice. Well, what temperature does it happen at? Well, you guessed right, 0 degrees Celsius. Okay, and right here, where this parallel line cross the liquid-gas interface, this is where in normal pressure, 1 atmosphere, liquid turning into gas or gas turning into liquid. Well, at what temperature does liquid turn into gas? This is the boiling point. So this is your boiling point. This is your freezing point. Yeah. And as you and you can see, you can change the temperature, you can change the pressure, and on this phase diagram and draw that same parallel line. You can have different crossing points and different temperatures, and you would be able to find, okay, different freezing point and boiling point of water under different pressure. Okay, so that's something that you could do here. Okay, now another thing that we want to also give you here is that the process of going between phases, crossing these phase interface, the 3 lines. Okay, now if you're going from solid to liquid, what's that process? Well, ice turning into water, what's that process? That's melting. Okay, what about liquid turning into ice? And obviously that's freezing. Okay, what about liquid turning into gas? That's the process of vaporization. Water turning into vapor. Okay, what about gas turning into liquid? That's called condensation. So different process of crossing the interface is called is having different names. Now, what about solid? And you can see at this part of the phase diagram, what really happens when you're crossing this line? You're actually turning directly from solid to gas, okay, without going through the liquid process. And from solid turning into gas directly, this is called sublimation. Okay, what about gas turning into solid? Okay, that process is called, this is probably the only thing that you don't know already. That's called deposition. Okay, so really we're not going too deep into the phase diagram, and this is kind of building up a little bit for the beginning of Chem 116. For those of you who's going to take Chem 116, Now, we're going to have a longer discussion about it in the first part of 116. But as of right now, everything that you need to know about phase diagram is introduced here. Okay, as long as you know what these processes are called, how to read a phase diagram, find your boiling point and freezing point at a given pressure, okay, and what does triple points means. Now, you should be good. All right, so that being said, let's go on to our final exam review of Chem 115. All right, so final exam of Chem 115 is going to be a cumulative exam, okay? And that means everything that we covered throughout the semester, okay, you have a chance, have a possibility to see. And again, I want to assure you one thing is that now, things that we didn't talk about our class have no chance of making it onto your exam, okay? And regardless of who's the instructor making those questions, I will make sure that before you actually see the exam, okay, those questions are written in the language that we use in our classes, okay? You don't have to worry about, okay, what if somebody wrote an exam that we didn't wrote a question that we didn't cover in our class? No, that's not your responsibility. I will make sure that doesn't happen. Okay, so we started the semester, and feels like an eternity ago, with chemical physical property. Okay, yeah. And really the difference between the two, it comes down to 3 words. For chemical properties, it always comes down to new stuff made. Did you make something new during the process? Okay, if you're only turning, let's say, water from one physical state to another, or you're only breaking glasses into pieces, okay, you didn't make anything new. Okay, the chemical makeup never changed, then it's a physical change. But if along the process, like you are turning grapes into wine, okay, or you're cooking food, okay, turning food cooked, okay, well, definitely along the way you made new stuff, okay, then it's a chemical change. So can you determine, given examples, what is a physical change, what is a chemical change? All right, intensive, extensive properties, and this comes down to actually 3 words as well. Does size matter? Okay, now, if size doesn't matter, okay, if your property is independent of size, like density, like hardness, like temperature, okay, then that property is intensive. So if the answer to this question is no, size don't matter, then it's intensive. But if your answer is yes, size does matter, okay, bigger size means of objects means higher value for this particular property, such as mass, okay, such as weight, such as energy, okay, then you're dealing with extensive property. Next topic. So given a particular property, can you put them into one of the two categories? Sig figs and scientific notation and the calculations that related to them. Okay, now can you count sig figs correctly? What are the rules of applying sig figs in your calculation? For addition subtraction, what rules do we follow? For multiplication and division, what rule do we follow? In a mixed calculation, how do we apply those rules? Okay, and chances are you're going to see something like that, and you had experience with that before. Okay, so can you do those calculations? And then another thing is, we did it together with this part. Now, conversion of different units. Okay, going from how to use your conversion factor. The way we do it, of course, is dimensional analysis, setting things up where the old units cancel and you lead it to the new units. And now, setting up your calculation correctly in this type of calculation, of course, is the most important. Making sure your units cancel rate, okay, and units in here pretty much dictates how are you going to do your calculation, whether it's a long conversion with multiple steps or if it's a simple conversion with one or two steps. All right, so after all of these initial introductory stuff, now place we really start to get into real chemistry is from the next topic. The atomic theory. Okay, now what is the atomic series all about? The four different propositions of Dalton. Okay. Substances are made up by little tiny particles that he called them the atoms. Okay, atoms are differentiated or characterized by their mass. Same type of atoms have the same mass. Different type of atoms have different mass. Okay, now atoms combine with each other in fixed whole number ratio to give compounds, and then in chemical reactions, compounds. There's no atoms being made or may disappear. It just shuffle and switch into different combinations. Those are Dalton's propositions. Now, and then, of course, from there, we learn more about things like the modern chemistry part of the atomic symbols. Okay, the letters representing different element. Okay, and well, let's not use this because this letter we already used for something else. Okay, and then atomic number, which represents the number of protons, so protons, and mass number, which represents the total of protons and neutrons, and then possible charge represents how many electrons lost or gained on this particular particle. So knowing what atomic symbol stands for, and going back and forth, if you have this many protons, this many neutrons, and this many electrons, can you write the symbol? Or if you're given the symbol, can you get those informations out of the symbol? Okay, and then we start to talk about a general introduction about the periodic table. Okay, and different groups, elements are in the same groups because they have similar and chemical and physical elements in the same group will have similar chemical and physical groups. And later on in the semester, now this is kind of what we did at the beginning of the semester is kind of an introductory type of mention of periodic table. Later on in the semester, when we get to the electron configuration part, our view of periodic table is more intensive. So if you have that information, okay, then you already know what you need to know about the periodic table we learned at the beginning of the semester. Okay, and then we also mentioned the concept of isotopes. Okay, same element, same atomic number, different mass number or different number of neutrons. Okay, and majority of the elements on the periodic table have different type of isotopes. And now, then after we introduce all these different atoms, we discussed atomic mass. Okay, the mass of different atoms, it's kind of a characterizing number for different elements, and the number, atomic mass value shown in your periodic table, which you're going to have a copy for the final exam, you're going to use a copy during the final exam. Okay, the atomic mass values in there are average atomic mass, and which is calculated by the total of all different naturally occurred isotopes, their percent abundance multiplied by individual isotopes and then put them all together. Okay, and can you do that calculation provided with the percent abundance and things like that? So the calculation about it. Okay, can you figure out average atomic mass? Or if you're given, let's say I have 3 different isotopes, okay, I'm given the average atomic mass, and I'm given, let's say, 2 of the 3 different isotopes atomic mass and the percentage. Can you figure out the third isotope's atomic mass? All of that is coming from the same equation. Just set it up. And after that, we go into the mole concept. Okay, now mole is a counting unit. Okay, it's just relating to a number, a huge number at that, the Avogadro's number. Okay, 6.022 times 10 to the 23rd. And now, can you convert, given the mass of compound, can you turn it into number of molecules or atoms, or given figuring out the mass of one atom or molecule using the Avogadro number and molar mass. Okay, and of course, we mentioned molar mass. Can you get the molar mass? Now, for atoms, molar mass is the atomic mass value that's provided in the periodic table. For molecules, molar mass is the total of all the atomic masses of everything in that molecule or in that chemical formula. Okay, so can you calculate molar mass? Figuring out molar mass. Okay, and with the molar mass, you can turn easily between grams and moles of things, which is a huge part in the later stoichiometry calculations. And now, one particular type of calculation, mass percentage of elements within compound. Given a chemical formula, let's say Na3PO4, can you figure out what's the percentage of sodium? What's the percentage of phosphorus? What's the percentage of oxygen in that compound? Regardless of how complicated the formula gets, it doesn't matter. Get your molar mass, put it on the bottom, and get the mass of your individual atoms, and multiply by whichever subscript they have, okay, and turn that into a percentage, and you're all set. And this mass percentage is a pretty useful way in figuring out the empirical formula of the compound. And now, to get, first of all, empirical formula. What is the empirical formula? This is not the actual chemical formula of a compound, okay? Now, one thing you want to be 100% sure is the actual formula of compound should be a whole number multiple of empirical formula. So if you have an empirical formula of CH2, okay, that doesn't mean, okay, that your molecule is made up by one carbon and two hydrogen, okay? Your actual chemical formula, your actual molecule could be, so empirical formula is CH2. Your actual formula could be a bunch of possibilities. It could be CH2, it could be C2H4, it could be C3H6, C4H8, the list can go on and on, okay? Empirical formula is the smallest whole number ratio of elements in a compound. All right, so how do we get empirical formula? We have a few different ways of doing it, okay? So a typical way to do it is from percentage of elements, okay? Now, if you have X percent of elements element A, Y percent of element B, Z% of element Z% of element C. Okay. How do you turn this into a empirical formula? So assume 100 grams of compound, and then you have X grams of A, Y grams of B, Z grams of C. Each of these can be turned into mole of A, mole of B, and mole of C. And then from there, once you get the mole, okay, divide everybody by the smallest number, trying to get a whole number ratio between the three elements. And that ratio, okay, let's say it's M to N to L. Then your chemical formula, your empirical formula for the compound will be A sub M, B sub N, and C sub L. So that's one way of getting your empirical formula. Now, another way that we learned is combustion or burning product. So you are having a compound sample and you turn them into, you burn it in oxygen, you turn them into different oxides, including carbon dioxide, including water, and if your compound have nitrogen in it, you could have some kind of a nitrogen oxide and whatever. Okay, now and then from the amount of each of the product, so from product, you could figure out the mole of your hydrogen, mole of your carbon, or mole of whatever other elements that you have. Okay, and then from there, once you got mole, then you try to get whole number ratio, and then your empirical formula. Okay, so at the end of the day, finding empirical formula goes down to mole of stuff. If I can find out each element's number of moles in my compound, then I'm all set. All right. Okay, so then we discussed conceptually what is an ionic compound, molecular compound. Okay, now what kind of bonds do they have? Ionic bonds is the electrostatic attraction between positive and negative ions, and in molecular bond you have covalent bonds. Okay, and of course for ionic bonds, the ionic compound, there's also a possibility of not only you have single monoatomic ions, you could also have polyatomic ions. Okay, now between the polyatomic ions, okay, such something like SO4 2 negative we're all very familiar with. Now, between sulfur and oxygen, there's still covalent bonds. Electrons still shared and everything. Okay, you learned Lewis structure. You're familiar with that. Okay, you understand that. But together, these guys shows a overall charge to the outside world, and that overall charge could be attracting or repelling, okay, other ions with positive or negative charges. And so general idea of what is an ionic compound and what is a molecular compound. And more than likely, for the ionic compound we deal with at this level, in this Chem 115 class, you're going to see some kind of metal, okay, and in your compound formula, And huge difference between ionic compound and molecular compound is that molecular compounds have their own individual discrete molecules. Okay, ionic compound is simply a ratio between positive and negative ions. Okay, so molecular compounds, you could see now the chemical formula of something like C2H4. Okay, it's not the smallest whole number ratio, but hey, that's my molecule. My molecule do have 2 carbon and 4 hydrogen in it. What can you do? Okay, but ionic compound, you would very rarely see those smallest ratio type of subscripts, because it's supposed to be the smallest whole number ratio of positive and negative ions. Unless, of course, when you have like complicated polyatomic ions like the mercury 1 ion Hg2 2 plus. But no, we'll talk about that when we get to the solution chemistry part. No. Then naming compounds, nomenclature. Okay, so how do you name ionic compounds? This is supposed to be easy. Okay, your metal name, okay, followed by your negative ion name, whether it's a monoatomic ion or a polyatomic ion. Those negative ions have their own names. The monoatomic ones, chlorides, okay, just use the root of your, so metal name plus root name of your non-metal and plus IDE, or you can replace that with polyatomic ion name. Sulfate, nitride, and so on and so forth. Yeah. And molecular compound, okay, how do you name them? Okay, remember now you have prefixes and suffixes. So first element, second element, how do we name them? Okay, we have rules to follow, and given a chemical formula, okay, you better be able to name them. Okay, so let's say for something like that. Okay, tetra, because of the 4, phosphorus, name of the first element. Okay, then hepta, okay, because of the number, ox for the root, and IDE for the second element. So tetraphosphorus heptoxide. And given a particular ionic compound, molecular compound, okay, can you name them? Okay, and also, one more thing about ionic compound naming is, okay, for your metals with fixed charges, you just need the metal name. Things like group 1A, sodium, lithium, you know they're only going to have +1 charge. Group 2A, okay, you know they're only going to have +2 charge. Or aluminum, you know it only have 3+ charge. Okay, so you don't need to worry about charge, but if it's transition metal, before you name your compound, you better figure out what kind of positive charge your metal has. Okay, so copper, so something like Cu2S. Okay, how do I know this is +1 charge? Because sulfide ion can only be -2 charge. Okay, So know those fixed charges, and then that means copper, each copper is plus 1 charge. So for copper is a transition metal, so make sure you have that Roman numeral, okay, in there before you can get the name out. So naming the chemical compounds, and of course, now there's also naming different acids, okay? Now, binary acids, oxy acids. How do we name them? Yeah. Given a chemical formula of a compound or an acid, can you give the proper chemical name of them? Or given those chemical names, can you figure out the chemical formula of your compounds? Okay, two possibilities of how that particular topic is going to be tested. Yeah. Then we talk about stoichiometry. Okay, now, and to be able to do stoichiometry, one thing is very, very important, and you have to have, and that is balanced chemical equation. So can you balance a given chemical equation? Now, can you make sure that when you're doing your stoichiometry, you have a balanced chemical equation if you're not provided with one? Okay, let's say you're given an unbalanced equation. Okay, remember to balance it before you can do any stoichiometry, because without those coefficients, stoichiometry can't be done. And the core process of stoichiometry, of course, is going from grams of one component of your reaction going to mole of that particular compound. Okay, and this is using molar mass of the compound. Okay, and then from the mole, you use the molar ratio. Where do I get the molar ratio? You get that from your balanced chemical equation, the coefficients. Okay, and you get the mole of a different component, whether it's a reactant product, don't matter. Okay, and then from there, using again the molar mass, okay, you could turn it into a different grams of the compound. So given amount of one component of the reaction, using the balanced chemical equation to figure out the amount of another component of the equation. That's what stoichiometry is focusing on. Okay, and then of course that's the very straightforward, simple type of stoichiometry. We also talked about two different, more complicated stoichiometry, and that is percent yield and limiting reagent. Can you do percent yield in the limiting reagent calculation? For percent yield equal to actual yield over theoretical yield times 100%. So the theoretical yield is what you calculate through the stoichiometry on paper. Okay, if every molecule of the reactant is turning into product, this is how much you can make. Okay, but the center of the idea in percent yield is that some of your reactants never made it to the product. They're either being wasted along the way or going through some side reaction, turning into something that's not in the main chemical reaction that you wanted to go through. But whatever it is, you wasted some. Okay, and then you ended up with the actual yield. So actual yield, okay, has nothing to do with your stoichiometry. Actual yield won't be calculated through your stoichiometry, starting from how much things that you were provided with. Okay, so can you do the type of percent yield calculation? And then limiting reagent. What's limiting reagent? How do I know this is a limiting reagent problem? Okay, amount of more than, oh, not mole, reactants provided. 1 or 2 or 3 or whatever, okay? And now, and because you're having 2 different amounts, okay? So there's always the possibility that one of them is not enough, okay? And the other one is too much, okay? So the limiting reagent process questions focus on, well, to figure that out. Which one is the limiting reagent? Okay, the way we use, okay, the standard way that we use is to calculate from the amounts of all your reactants to the same product. No, not products. Product. Okay, and whichever reactant produces the least amount of product is your limiting reagent. Okay, and once you figured out in that process what is the limiting reagent, then the whole process simplifies. Okay, because you want the amount of one of the products, just start your stoichiometry from the limiting reagent. Okay, you want to go to figure out how much of the other reactant provided, okay, has left over. All you need to do is go from your limiting reagent to figure out how much of the, through stoichiometry, how much of the other reactant you actually use, and then subtracting the value. Okay, so both of these 2 types of calculations you have intensive practice on. So no, it's a longer calculation, okay, than regular stoichiometry, but I don't expect you to have too much trouble with it. So then we start about solution chemistry. Okay, now what is a solution? Okay, this is different compounds, solute and solvent, okay, mixed with each other at a molecular level, okay, and the solutes that we learned has electrolytes. What are electrolytes? And non-electrolytes. Electrolytes is something that when you dissolve it in water, it could conduct electricity. Okay, non-electrolyte, of course, is the opposite. No. Okay, why can your electrolyte solution conduct electricity? Okay, now, obviously because you made some charged particles. Okay, and depending on how much charged particles you make, okay, we can divide electrolytes into strong electrolytes and weak electrolytes. Okay, both of them dissociate. Okay, the only difference is strong electrolyte dissociate 100%, and weak electrolyte dissociate less than 100%. No. And what kind of things are strong electrolytes? You have strong acids. No. You have 7 of them. Okay, what are they? Make sure you know them. Strong base. You have 8 of them. Okay, what are they? 5 in group 1A, lithium all the way to cesium, and then 3 more in group 2A, calcium, strontium, barium. So 5 and 3, total of 8, and soluble salts, and that of course goes down to your solubility rule. Got to be able to judge a given compound, ionic compound. whether it's soluble or insoluble. And weak electrolytes, you can also break down into two categories. Strong acid, we don't have a number on it now. Any acid that you've seen that's not one of those 7 strong acids is a weak acid. Okay, and then you have, no, not strong acid, weak acid. And then you would have also weak base. And we really just talked about one type of weak base, which is ammonia. Okay, no. And now, then something related to this is the dissociation of electrolytes, okay? Because it affects a bunch of things, like the concentration of things, and you know, and when you have, let's say, something like Al2 SO4 3, okay. First of all, you need to be able to judge that this is a soluble salt using your solubility rules. Okay, then you got to realize that you're going to have a bunch of ions. Okay, now, and subscripts now becomes the free ions. So 1 mole of this ended up with 2 mole of positive ion and 3 mole of negative ion. Okay, and that's your full dissociation. And then for the weak electrolytes, of course, now we don't need you to know exactly how much ions are produced, but we need you to know that, okay, let's say I have 1 mole of HF. The dissociation is going to be into H plus ion and F ion, but you have way less than 1 mole. So 1 mole of HF, you would have way less than 1 mole of fluoride ion. Majority of your compounds, okay, stay in the form of a free molecule, okay, moving about in the solution. Okay, now then we discussed double displacement reaction. And net ionic equation. So you have 2 ionic compounds, 2 electrolytes, exchanging partners to make new. Now, so can you predict product? Okay. And of course, balance your equation. And then once you get molecular equation, can you do the right dissociation? Okay, only dissociate strong electrolytes. Now, so if it's acid, I only break down strong acid. If it's a base, I only dissociate strong base. If it's a salt ionic compound, I only dissociate the soluble ones. Okay, and then cancel spectator to get your net ionic equation. Okay, now can you do these things and get the correct net ionic equation in that process? pretty big topic there. Okay, applies everything you learned about solution chemistry conceptually about solution chemistry at that point. Okay, and then we'll talk about the mass part of solution chemistry. Now, concentration, of course, in molarity. Okay, not only about a compound, could be also be about your ions. Okay, now between, so molarity equals to moles of solute in liters of solution. So out of the three things, if you know two, can you figure out the other one? Okay, and can you find how many grams of solute you need to make a certain amount of solution with a particular concentration? And now, then the calculations we did also includes dilution. Okay, that's the kind of thing that you do M1V1, M2V2. That's easy. Okay. Solution stoichiometry. Okay. You have a chemical reaction happening. Okay. And this is like typically the titration stuff is part of it. Okay. Now, and make sure that you don't take your M1V1, M2V2 into this. Okay. In an exam question, doing M1V1, M2V2 for a solution stoichiometry problem almost guarantee you get one of the typical wrong answers. Okay, so the correct way of solving it, of course, is do your balanced equation. Okay, and then go from concentration and volume of the component that you know, turn it into moles of stuff, and then do stoichiometry. To turn into mole of the other component, and from there, okay, with mole and with maybe concentration, maybe volume, and you can find your final result, what you're looking for. Okay, and the last solution chemistry calculation we also discussed is common ion concentration of mixture solution. So let's say you have 20 milliliter of 2 mole NaCl plus 15 milliliter of 1.5 molar BaCl2, then 25 milliliter of 1.2 molar AlCl3, and find chloride concentration in its mixture. That type of calculation. And we had examples, you have seen quiz and exam questions like this. Make sure you know how to handle this. Find out the moles of chloride ion individually in each solution, add them together, and divide by the total volume. Okay, so let's finish here, and our next video lecture, we're going to finish our entire topic list, review topic list for Chem 115.